So for our project, we choose to do a CFD analysis on a 1976 Toyota Hilux. So there's 4 different variants, one with the tailgate up, tailgate down, with a tonneau cover, and then with air scoops on the side. So for our personal interest in this project, I've never done anything with CFD before, so I was really interested just to kind of get into it and learn a new skill. And also for ours, because I really want to see how like a simple changes could impact the drag force on a truck. Because in this case, it's just tailgate up, down, very simple changes. So I was really interested to see how that, what impact that would have.
My personal interests were expanding my knowledge on CFD. I had done it a little bit before and liked it a lot. I hadn't had the chance to do it again, so I saw this as a good opportunity to go back to it. And it is one of the only things that I have used at my employer consistently, so it was nice to get to learn a little bit more. And improving efficiency of vehicles is something that is very common in today's world in the automakers, and I would like to work for an automaker or a racing team ideally at some point, and this is a very useful subject for any mechanical engineer in automotive design.
So we had 4 main goals. We wanted to use CFD to show pressure and velocity distributions for each of the variants. And then from that, we can easily find the drag coefficient, drag force, and then make conclusions on which variant is most efficient. So our model is a 1976 Toyota Hilux. It's a scale model. And like I said earlier, 4 different variants: tailgate up, tailgate down, tonneau cover, and then we added these air scoops on the side. And we'll get into that in the next slide. So we made a design modification which was these air scoops, and the goal with these was to attempt to fill in the low pressure area in the truck bed. So originally we wanted to use a scale F-150 model. We found a perfect scale model, but we had a lot of issues just working with it, and we got a lot of geometry errors when we tried to put it into the fluid simulation in SolidWorks. So ultimately we had to find a simpler model. So we started with this Toyota Hilux. However, because the model is a lot simpler, there's some potential accuracy issues because the model isn't exactly representative of real Toyota Hilux. And as you can see here too, the bottom of the truck, it doesn't have any of the features, any driveline that a real truck would have, so this will impact the results.
Yep. Another problem with the F-150 model, if we could have imported it successfully into the flow simulation software, it would have had a lot of elements and a lot of channels where the air could have gone through, and it would have taken a lot more to complete the calculations. And since we are running, as you'll see, 4 speeds with 4 different versions of the truck, we did have to do a lot of different simulations. So, as I was saying, the CFD issues encountered, beside having to use a simpler model, the computational power and time constraints limited the ability of using a lot of precision, as we tried to simulate it with a higher mesh, a higher refined mesh, and instead of taking, say, 20 minutes like our models took, it bumped up to 9 hours, which for calculating 16 different models, then it couldn't have been possible.
And so one of the most important things with using a fluid simulation is establishing the proper boundary conditions. This is something that we learned early on. Because early on we had boundary conditions that were roughly maybe about 2 times as long, 2 times as wide as the truck. There's an issue with that we'll get into later. So what we ended up doing is for computational domain, it's roughly 5 times as wide, 5 times as tall, and 15 times as long as the truck from the rear. And having it extra long in the rear is the most important because then we can watch the velocity profile eventually go to 0. And for this domain, on the outer surfaces of the domain, that's where the pressure is equal to atmospheric pressure and the velocity is equal to 0. And we're assuming a no-slip boundary condition on the outsides of the truck.
Okay, so for the setup of the simulation, if you want to come up close since it's little, first you import your model into your desired modeling software. It has an automatic setup for the simulations. You click Wizard up top here, and it opens up a few different menus where you can select your conditions, your units, your velocities, your inputs, your everything. And a few of the things we did here, everything we kept basically the same. We selected our units. We are only doing a fluid flow simulation, and we decided to exclude the internal space of the model since we are doing an external fluid simulation. We selected our fluid to be simulated, which in this case is air. And for our computational domain, as Jake said, we asked the Dean of Engineering for an estimate of how big our computational domain should be, and this is a visualization of it. Then we needed to modify our meshes, as we said. Here's a slider. The software is very easy to use, so it gives you sliders, it gives you menus. We went kind of in the middle of the refinement, because if not, it would take a lot of time. And we decided to insert a local mesh, which is a more refined mesh around the model of the car, around the more important areas, so we could have a little increased accuracy, but not compute it as fine in the other places. Then the software lets you select all your goals, all your values that you want to see. We selected all our important pressures, velocities, densities, and then you can run the simulation after selecting what values you wanted to give you. We also had to insert a calculation for the drag coefficient since the software didn't calculate it. So we used our force in the z direction, which is our drag. We used our average density of the fluid within the computational domain as our density, since it would change in different places, and our velocities that we were running the air at.
And this is just a quick summary of our initial conditions. So we're going from 40 to 70 miles per hour in 10 mile per hour intervals. We're using air. Of course, our atmospheric pressure will be 103 kilopascals, and our air temperature is at 293.2 kelvins, which is 20 degrees Celsius. If you want to come up here, you can see the mesh quality. So around this green box here is essentially around the truck. It's where the mesh is going to be the most refined. So if you compare, like looking out here, the mesh is extremely coarse, and the closer you get to the truck, it becomes very fine. So that's what the local mesh establishes. And here we took a look at the streamlines within the bed of the truck. Here we have the tailgate up, down, tonneau cover with the air guides. I think the most interesting thing from here is comparing the tailgate up to the one with the air guides. As you can see, there's a much higher velocity in the model with the air guides because it's feeding the air into the bed of the truck. And we're going to illustrate this again later on in the presentation.
Okay, so one of the benefits of using the software is that we can visualize our results in many different ways. This one are the relative pressure contours at 40 miles an hour. And so the most important things here are to see the low and high pressure zones. They're different sizes, which is what will at the end affect the most for the drag coefficient. We can see that this one is tailgate up, tailgate down, tonneau cover, and our air guide modification. Mm-hmm. And you can see that air guides channels a lot of air into the bed of the truck, which reduces the low pressure zone compared to the tailgate up and tailgate down. And we can see that also the tonneau cover also reduces that low pressure zone since there is less place for the air to create vortices. This is the same contours at a higher speed, 50 miles an hour. And I intentionally bumped up the lower bound of the pressure so you could better visualize where it has low pressure, where it has low pressure, high pressure. But the results are pretty consistent with all of the models, just the maximum pressures go up as the speed goes up. And this is of the same truck, the tonneau covers, at 40, 50, 60, and 70 miles an hour. Just another way to show how the low and high pressure zones expand as the speed goes up.
And here are wind velocity contours. So on the top here is tailgate up, tailgate down, tonneau cover with the air scoops. And so of course we know that right in front of the truck for all these will be the stagnation points. Velocity will be equal to 0 at that point. And a thing to, I guess to take note of is the velocity profile right behind the truck and along the bed.
Right.
The same contours at different speeds.
Yep.
And a comparison.
Yep, and here we're comparing the tonneau cover from 40, 50, 60, and 70 miles per hour. So we can see the general velocity profile of the bed remains the same, but of course at the top here, where the velocity is at its highest point, the area will increase with speed.
Okay, so this is the calculation for drag coefficients. This is the result we wanted to get from this, as a lower drag coefficient will result in increased fuel economy in a real car. And we're comparing them at highway speeds at 70 miles an hour. The tailgate up gives a drag coefficient of 0.387. Tailgate down increases the drag coefficient by quite a bit, 0.401, which would seem counterintuitive. At the beginning of the project, I thought that with the tailgate down, the airflow would be better than with the tailgate up, as there isn't something stopping the airflow. So that was a surprising one to see, but we were warned by this at the beginning, warned about this at the beginning. Then with the tonneau cover, we actually get the lowest drag coefficient. It seems that the way it stops from creating vortices helped to reduce the drag force by a lot. And air scoops gives us a similar coefficient to tailgate down. It was a bit higher than tailgate up, which told us that the modification wasn't really good for reducing drag force, but it was still something interesting to see.
And here's the drag force for each model. As Inti was saying previously, the tonneau cover is going to have the lowest drag force compared to all the other variants.
Right.
We can visualize this in the next slide with a graph. And so here's just the graph of each point of the drag force and the velocity. This helps to illustrate to see the difference between each of the four variants. You can see the tonneau cover is by far the best, with the worst being the tailgate down.
So our final thoughts. The lessons I personally learned from the project are that CFD is a very useful tool. We could not have possibly calculated all of these values by hand, so learning to use a tool to get to them was extremely useful. And this is something that will open a lot of doors with getting into car manufacturers. And the value of the project to fluid mechanics is, as I said, a lot of the things that you will want to calculate using fluid mechanics will not be possible to calculate by hand. So using and learning a CFD software was very useful. And I believe a project using CFD, or just any kind of project like our teammates did, is something that should stay in the course, as we get to learn something that interests us and we don't necessarily see in the class, but it also relates to the class very well.
I had similar thoughts because for this I never did anything of CFD, so it's a whole new tool in my toolbox that I can use in the future. I think it's super valuable in helping to understand different fluid concepts, because in the book we have pictures of streamlines and different illustrations in class, but it's really hard to actually kind of picture what that actually means, or what that even looks like without CFD. And so for those reasons, I think it definitely should be required for upcoming class. I think it's very valuable. Do we want to show that?
Yeah, we're going to show a animation of the streamlines going in the bed with the air guides. We thought it was the coolest one, since there are some not just vertical but horizontal vortices created. Yeah.
Yep, so we can see here how, or you want to talk since?
Oh, yeah. Okay. We can see how a lot of air is channeled into the bed through the scoops. We can see, as we saw in our velocity plots, how the wind speeds up a lot by the roof of the truck. And we can see the low pressure or air bubble zone created in the bed of all of the models, but the air scoops really, they make it bigger. Yeah. We can see the vortices created in the X and Y dimensions. You want to add anything?
Do we want to show the other ones or no?
You want to show the tonneau cover one? Is it loaded?
Sure. Yeah, I have it up.
And this is the visualization of the streamlines with the tonneau cover. As we can see, the software didn't detect enough vortices on top of the tonneau cover that it didn't even show them. But we can still see the lower velocity on the bottom, higher velocity on the top. Good illustration.
Excellent.
Thank you. Yeah. So that's it.
Yep, and that concludes our report.
Project. Thank you very much. Are there any questions?
Any questions, guys?
Do you think if with the air funnels, if you had the trunk down again, do you think it would perform better? Or the tailgate.
The tailgate down. Oh, that's a good point. Yeah, because channeling in air and the tailgate down would, yeah, that would be something interesting. Yeah, didn't think of that combination. Yeah.
How did you guys get your model?
We found it online, and then we just modified it with the air scoops and the tailgate up and down in the tonneau cover.
Yeah, and we did have a little problem at the beginning. It looked like the windshield and the back glass weren't connected to the rest of the truck, so we could see when we plotted the streams that it went through the cab, so we had to build another body around it so to make sure that that wouldn't happen.
Okay. All right. Good job.
Thank you.